Well, today we have kind of an informal meeting since there's nobody here. But at least that means I get to take my mask off and maybe you can hear me clearly for a change and get to see what I look like so you know who to say hi to in the fall when you come back. I so miss being able to meet you and find out what you're like. Today we're going to pick up where we were, and I thought I'd open with this preliminary discussion and say, well, what's the definition of a circle, right? It's the locus of all points or set of all points at a fixed distance from a given point called the center, right? So if I just take a fixed length string and put it attached at one point, here's the locus of all points at a given distance from the point I call the center. And I can draw a pretty good circle that way. But now, how do you draw an ellipse, right? Trick is to know that ellipse has a similar definition. It's the locus of all points. I had a better blackboard with not so much chalk on it. This works very well, but on this one, I don't know. It's a set of all points such that the sum of the distances from two foci, here they are, is constant, right? So this string keeps it a constant distance. This one plus this one is always the same distance. So all I have to do is hold my chalk at the end of the string. Keep this thing attached despite the chalk. It usually works pretty well. I can draw a pretty good ellipse. How about that? Better than my circle than the thing came loose, at least. And if I spot the foci here, I have the points that I used to help make it too. All right, so there's a kind of a fun thing just to kind of wake you up. Maybe some of your teachers will use an illustration in the future. There's a great way, I think they said Kepler used to draw parabolas with a t-square. So it'd be fun to do that sometime. Huh? All right, today we're going to continue what we were doing last time about homogeneous linear second order ordinary differential equations with constant coefficients. Continued. How about that? We said that's a mouthful. I had to write it up beforehand so I don't take 5 minutes getting started here. And what are these? These are the following kinds of equations, right? They're differential equations that look at this form. A times y double prime plus b times y prime plus c times y equals 0, right? So that's the equation we want to look at, call it number 1, where a, b, and c are constants, hence the name constant coefficients. This is what we called a linear equation before. We said a linear equation was homogeneous if the right-hand side was 0, and then constant coefficients just means you multiply each of these by a constant a, b, and c. The a, b, and c we said are picked with forethought because what happens is when you plug in a test solution, e to the RT, you deduce, we did it, we proof, that e to the RT is a solution if and only if R satisfies the so-called characteristic equation for this. By the way, I should mention that this is probably the most important second order equation that you have to solve. Is constant coefficients. It's used a lot in basic introductory courses in all sorts of scientific fields. So just like we said, separation of variables and linear equations were probably the two you'd use the most when you get out of here for first order equations. This is probably the one you use the most for second order equations when you get out. The characteristic equation you get by plugging this test solution in is just a quadratic equation with the same coefficients, a, b, and c. AR squared plus BR plus C equals 0. And so all I have to do to try and find some solutions to this differential equation is solve my quadratic equation of linear algebra or algebra. So this has easy solutions. in three cases. One, It can have R1 and R2 real and not equal. Let's put it that way. It can have R1 equal to R2 real numbers. Or the third possibility is that R1 and R2 are complex conjugates, a number, let's say alpha, plus or minus another number I beta. So there's two solutions here, and they have an imaginary part, I denoting the square root of -1. We said in the first case, this is great because what happens is since e to the RT is a solution if and only if it satisfies this equation, we find R1 and R2 are two different real numbers for which that works. This is what we can do. One, if R1 is not equal to R2 is real, then Y1 equals e to the R1t, Y2 equals e to the R2t are both solutions. And furthermore, you can use the Wronskian to show that they're independent. You don't have to do this on your homework problems because you just memorize that if they aren't equal, they're independent. Here's the proof. E to the R1t, e to the R2t. Remember the Wronskian? The Wronskian of these two functions. You put them on the first line, you put their derivative on the second line. R1 e to the R1t, R2 e to the R2t. The Wronskian is this times this minus this times this, right? Diagonal minus diagonal. It's just the determinant formula you learned from calculus, but Wronskian has these functions in it. So this times this is R2 e to the R1t e to the R2t, and then this times this is R1 e to the R1t e to the R2t, and when you simplify this, it becomes R2 minus R1 times, well, these can be combined into e to the R1t plus R2t or R1 plus R2 times t, right? And same thing here. And so what you have is R2 times that minus R1 times that is R2 minus R1 times e to the R1 plus R2t. Well, remember the theorem we had says the Wronskian is either zero in the whole interval or not zero in the whole interval, non-zero in the whole interval when these things are solutions of an equation like this. And if they're not zero, these are independent solutions, and if they are zero, they're dependent solutions. Well, how can they be independent or dependent? This is never equal to zero, right? E to a number is always positive. So this is positive. The only way we make this times this, the product zero, is if this is zero. So the way to make them dependent is only if R1 equals R2, in which case you've got the same solution. Duh, right? So they are, of course, dependent. They're equal. So what happens now that R1 is not equal to R2, then that's not zero. And we have two independent solutions in our theorem from last time, which we didn't prove because it's too long and involves advanced notions of vector spaces of functions. Is that these are solutions. E to the R1, independent solutions. E to the R1t and e to the R2t are also independent. That's then implies that y equals C1 e to the R1t plus C2 e to the R2t is the general solution, the form of all solutions, written as a linear combination of constant times one plus a constant times the other. So that's the first case. We already talked about that. But I just wanted to remind you so you know where we are and where we're going. Every time I sleep on something, I can't remember a lot of details. And we had an example. Let me give one more just to be a little more reminding because it's so similar to what we're going to do next. Here's the example of this case again. Suppose I have y double prime minus 5 y prime plus 6y equals 0. Here's a second order linear differential equation with constant coefficients. Think of a 1 being here. That's A, B, and C. What do we do to solve this? We write down the characteristic equation, which is the same thing with r squared replacing y double prime, r replacing y prime, and 1 replacing y. So it's AR squared plus BR plus C equals 0. Plus A, B, C. And consequently, the solutions immediately are by the quadratic formula, or you can factor it in this case, since it happens to be easy. R minus 3 times R minus 2 equals 0. Right? Which means that there's exactly two solutions. The zero product property says that this product is 0 if and only if at least one of the factors is 0. So either R is equal to 3 or R is equal to 2. Two solutions. So we'll call this one R1 and call this one R2. And now we'll say, therefore, the general solution is y equals e to the 3t times C1 plus e to the 2t times C2. Just put R1 here and R2 here. This is a solution. This is a solution. We just showed that as long as R1 and R2 aren't equal, these are independent. So this is the general solution. Every solution can be written in this form. All right, so that's the first case. But now the question arises, well, what if R1 and R2 are equal? Here's the second case. R1 equals R2 are real numbers. Now what you do is you say, well, maybe I can get lucky and guess again. And in fact, you can. We're going to find a way to deduce this without being lucky later. But for now, we'll just note you can plug in. I guess I should say one thing first. Y1 equals e to the R1t is still a solution, right? We proved it. R1 and R2 are both solutions. It's just when they're both equal, then it's only one linearly independent solution. So we just need one more. By plugging in, you can see for now, like I said, we'll get a method that derives it later if you prefer that. Y2 equals t e to the R1t is also just check by plugging in. That's a proof that it's a solution. Even if it's not an insightful one. All right. Wait a minute. I have two independent solutions. If you put this in the Wronskian, you'll find out the determinant is not, the Wronskian is not 0. So therefore, immediately y equals C1 e to the R1t plus C2t e to the R1t, R1 equal R2, right, is the general solution. How about that? Easy as that. Sometimes people prefer to group these together. I just want you to be sure. You can write it as y equals C2t plus C1 all times e to the R1t. That's kind of a nice, more compact way to put it. This one displays that it's a nice linear combination and therefore the general solution. Better than this one does, but this one's, like I say, shorter. Let's do an example of that just to have done one. Suppose I give you this differential equation. Y double prime plus 6y prime plus 9y equals 0. I believe this is the one in the notes there. How do I solve that? Write the characteristic equation. Just replacing this with r squared, this with r, and this one with 1 is r squared plus 6r plus 9 equals 0. Then you solve that for R1 and R2 and immediately write down the solution again. Well, let's see. This is equivalently, by factoring again, since it's easy, R plus 3 times R plus 3 equals 0, which says that R, either this is 0 or this is 0. So either R is equal to -3 or R is equal to -3 again. there's only one solution. Remember the quadratic formula would show you that too. It can have two distinct real solutions. It can have exactly two equal real solutions. That's what we got in this case. Or it can have two complex conjugate solutions. All right, so R1 and R2 are equal. So now what we say immediately is the solution y equals C1 times e to the R1t, the one solution we know from this, plus the one we can deduce by plugging in and checking, C2t e to the minus 3t. There's the general solution for that one. It's just as easy as the first method. You just have to remember multiply by t. All right. Well, what about the last case? That's the hard one. It's not so terrible. Suppose that R1 and R2 are complex conjugates, alpha plus or minus I beta. These are just two fixed numbers, alpha and beta, that you get from solving the characteristic equation. What do I do now? This is where you appeal to complex numbers. Those of you that are going to be electronics engineers are going to, this should appeal to you because as you go through electronics engineering, there's actually a lot of complex stuff coming in. Not a great deal, but enough that it's really worth reviewing your complex numbers. Suppose instead of looking for real valued functions that satisfy the differential equation, we look for complex valued functions. Then if you really think about it, y1 equals e to the r1t is e to the alpha plus I beta times t is still a solution, right? You plug it into the differential equation. The proof we did before still applies. You plug this in the differential equation, you see it's a solution. And it's just you have an imaginary unit I in here. And so it's kind of dissatisfying when you give that to your boss. The electronic circuit does this. That's imaginary, right? Imaginary. Well, by the way, electronics engineers also don't like this I. They use I for current. So they'll use J for the square root of -1 in your electronics book if you're doing it. So there's one solution, still overall complex valued functions. And now you have to remember Euler's formula. We talked about Euler before, right? Boy, is he one of the famous mathematicians of all time. Euler's formula says this, that if you have e to I times theta, you can rewrite it, and it has to look like this. It's cosine theta plus I sine theta. And you might say, well, why is it equal to that? Where do you pull that from? Right? Imaginary number out of the magic hat, right? Well, actually what it comes from is if you write down the Maclaurin series for this, if you demand that e to a complex number has the same Maclaurin series, right? Like e to the x is this, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And you put I theta for x, right? You can group the terms properly and show that actually it comes out to be this. So that's one reason it should be that, is if you want it to have the same Maclaurin series, right? So Euler's formula says you should replace e to the I theta with this. And that's really what you need anyway. If you want to be able to take derivatives, you'd like it to have a nice way of taking derivatives, such as Maclaurin formula. So we'll use that definition, and then we see that y1 actually can be written like this, right? This is e to the alpha t times e to the I beta t, once again, assuming that these exponents with real and imaginary parts have the same properties of exponentials, and they will if you follow this Maclaurin series thing. Now you can say this is e to the alpha t times, and use this as theta cosine beta t plus I sine beta t. And indeed, if you plug this into the differential equation, take the derivatives and just treat I as a constant, you'll find out this is in fact a solution. All that works. And there is a solution. The only problem is this imaginary unit here isn't real, right? Well, we can fix that, right? Now, what about the other solution? Y2, similarly, we should point this out. If I took e to the minus I theta, what do I get from that? Well, that's the same as e to the I times minus theta, which is cosine minus theta plus I sine minus theta by Euler's formula again, just following it. And then cosine is an even function, the minus goes away. But sine is an odd function, the minus comes out. So e to the minus I theta has this form in order to satisfy Euler's formula. And if I take that e to the alpha minus I theta t, the second solution we deduced by plugging the test function e to the RT into the differential equation, this is going to be e to the alpha t times e to the minus I beta t. Maybe I better write it out. I hate to put it in the way is all. I'm going to put it here. E to the alpha t times e to the minus I beta t. But that one comes out as cosine minus I sine. So this is e to the alpha t cosine beta t minus I sine. And now comes the magic. What if I were to take y1 minus y2? Remember that first term we did on these solutions to linear equations says that if you take a linear combination of solutions, it's again a solution. So since y1 and y2 are solutions, so will y1 minus y2 because it's 1 times this one plus minus 1 times this one. It's a linear combination of the two. So I can subtract these two and get a solution. Moreover, I'm going to try and do something a little nicer. I'm going to take these and divide by 2. Now I've got 1/2 y1 minus 1/2 y2. That's also a linear combination of y1 and y2. It will be a solution, right? Constant times 1 plus constant times the other. So what do I get when I take that? Well, I get 1/2 this one, which is 1/2 e to the alpha t cosine beta t plus 1/2 I e to the alpha t sine beta t. That's just 1/2 this one multiplied out, right? Like a half, this times a half, and this times a half. That's 1/2 y1. Then minus 1/2 y2, so I need to take minus 1/2, and I multiply 1/2 times this one, and multiply that is e to the alpha t cosine. This one, sorry, minus 1/2 I e to the alpha t sine. So y1 minus y2 over 2 is this, 1/2 the first one, minus this, 1/2 the second one. So put a parenthesis there. Now something great happens. This is what I wanted. The imaginary parts cancel. This one cancels this one, and there's no more I. I actually get 1/2 this one. Oops. This, I'm sorry, this is supposed to be plus. I'm sorry. Add these over 2. Sorry, let's review the video. If I add them over 2, then this one cancels this one, and I get this one. Here's the first one, plus the second one, added. 1/2 the first one plus 1/2 the second one added. Now these two cancel. And I get this plus this is 1/2 of this one plus 1/2 of this one is e to the alpha t cosine beta t. What I've shown is that this is also a solution, but now the i's are gone. So this is a solution to the differential equation, and this one is real. By taking a clever linear combination to make the imaginary parts fall out. Well, now you can, based on that success, try another trick. Maybe if I subtracted these, I could get something to cancel out, right? If I took y1 minus y2 over 2, well, what would I get? I take this one minus this one, and now the cosine parts would cancel, right? This times this would cancel, this times this, so the cosines would cancel. And I get this one minus this one would be 2i sine beta t. times e to the alpha t. So I get this, right, all over 2. I get twice, well, I get I should write some more steps, huh? You get this times a half would be 1/2. Let's just write it out. E to the alpha t cosine beta t plus 1/2 e to the alpha t sine beta t. Except it's not 1/2. Well, yeah, okay. So it's 1/2 and 1/2. That's 1/2 the first one. And this time I'll subtract 1/2 the second. So I'll subtract 1/2 e to the alpha t cosine beta t minus 1/2 e to the alpha t sine beta t. And once again, I get things to cancel. Now this one cancels this one. And I'm left with, and I forgot the I. I'm left with this plus this gives me 1/2 of this and 1/2 of this is 1 whole is I e to the alpha t sine beta t. So subtracting and divided by 2 also gets something to cancel, but unfortunately it doesn't get rid of the imaginary I. However, if I would have done one more thing, if I would have divided this by I, then this one gets divided by I. These still cancel. And since the i's cancel, this one, the i's cancel here and here, I wind up with this. So if I take y1 minus y2 over 2i, I find out this is a solution and this is also real. If you plug these into the Wronskian, you can show, just like we did with that first example, that these are independent functions. Let's not do it, it takes too long. But if we have 2 independent solutions, our big theorem, granddaddy theorem I called it last time, is this, that the general solution is an arbitrary linear combination. So I take C1 times this first solution, e to the alpha t cosine beta t, plus C2 times the second one, e to the alpha t sine beta t. This, in fact, is the general solution of the differential equation. 2 independent solutions given an arbitrary linear combination. Doesn't matter what C1 and C2 I pick, I get a solution. I get all solutions by letting those be arbitrary. There is actually an interesting thing to say here. What if I was trying to solve for complex valued functions, right? Functions that have a real and an imaginary part. By the way, just to remind you on complex numbers, right? If I say z, a complex number, is 3 plus 2i, we say that this number, the real number without the I, is the real part of the complex number. And the number that multiplies I is called the imaginary part. It's not actually an imaginary number itself, it's the real number that multiplies I. So when I refer to the real and imaginary parts, I mean the part that has no I in it, and the real part that multiplies I. There's no more, neither of these have any I in them. Now, I'm starting to make a point here. What if we were trying to solve for complex valued solutions? Isn't this, by my proof, still all complex valued solutions? Where have we gone wrong? All the i's are gone, right? This is actually all complex valued solutions. But the idea is you have to let all your arbitrary linear combinations be complex numbers. So this is all complex valued solutions. Even though I don't see an I in there. Because the idea is in complex numbers, you have to let the constants be complex number too. So it's by letting C1 and C2 represent arbitrary complex the I comes out of those. And so what we've done is found the general solution over all complex valued functions. But wait a minute. We just said these two functions here, without the C1 and C2 are real functions, real valued functions, right? There's no I in there. That are solutions to the differential equation. So I can take an arbitrary linear combination using all real numbers and get all real valued solutions. Let's call it A. So this is actually all real valued functions, what the engineer finally wants. All real valued solutions by letting C1 and C2 represent arbitrary real numbers. And if you really think about it, remember the real numbers are a subset of the complex numbers, right? If I write a complex number 2 plus 3i or whatever, and in general, A plus BI, the real numbers are the set of all complex numbers where B is 0, right? So the real numbers are a subset of the complex numbers. And what we're finding here is by letting C1 and C2 be only real numbers, we get all real valued solutions, the subset of this set that's real valued. So nicely, you can find all complex value solutions. You write this down and say C1 and C2 are arbitrary complex numbers. Or you can find all real value solutions. You write down the